Okay.
So yeah, go ahead.
Yeah, so I'd be glad to hear you talk about your stuff. The guy on the N category cafe helped me figure out what the Néron Severi group is for.
Was this Francis?
Yeah, this guy Francis. His name is Francis Bischoff, actually, I think. And okay. Yeah, so maybe you saw that. I think I almost
I didn't completely follow it, but go ahead, yeah.
Yeah, I almost understand it. There's just one step that I'm not sure about, but it's a nice application of this exponential sequence in sheaf cohomology. And so I think I understand a bunch of stuff, but the upshot is that it settles the question of how the pattern continues as we go from the version for line bundles to the version for gerbes and so on. And your guess was the correct one. It keeps expanding out. So we look at the integral cohomology intersected with the Dobot cohomologies of that same total degree, except for the two end ones. So that's the short version of the story.
Right. Sorry.
But it's sort of nice to know why it actually works that way.
Sure, but are you saying you do understand? Because I don't understand it.
I understand it, except for one fact that I believe. I mean, I believe he's probably right, but I don't quite see why it's true. So, but it's just a small, one extra thing.
I mean, I have a lot of ideas about how to understand it, but I also have a lot of problems. But like I say, I'm very disorganized. Okay, today's the 4th. And what am I trying to say? So in that same discussion, so this is your holomorphic gerbes thread on the N category cafe. I think the first response was from Tim Hosgood, is that right?
Yep.
And okay, so you mentioned some volume on Bailensen's. Oh, remember what I mean, there was some paper in that volume you mentioned, and he said it was like the standard reference or something like that on that topic or something like that. I can't remember the name. Fiveg.
Yeah, so I guess you mean Brzezinski's paper, holomorphic gerbes and the Bailensen regulator.
Well, no, but it wasn't just that paper. I mean, that was, but there was a volume. There was
right. Yeah. Okay. Yeah. So he said it's oh no, sorry, it's a completely different one. So he said the paper I mentioned by Essenwalt and Viveg.
Okay, yeah.
Is, quote, the reference for Dolan cohomology.
Aha, okay. Okay, so that's interesting. That's very interesting. I looked, the NLab gives you access to that volume. And I looked a little bit at that particular paper, and really, again, it really did not, at this point, it just made my eyes glaze over. Maybe, maybe I'll be good to be able to get something out of it later. But at this point, it just made my eyes glaze over. But I happened to glance at another paper in that same volume by Heap and Vazelman or something, HEEP. And that was much, much more interesting to me at this point. And it was interesting because they were very very blatantly, explicitly talking about motives and how the motives were related to the Dolan cohomology. Now, I'm sure I could find, people who are claiming to explain motives or something like that, but somehow this was more interesting to me. People trying to use motives to actually explain Dolan cohomology and stuff like that. So I just wanted to mention that's the thing from that discussion so far that has been most helpful to me so far. Let's see. So there was another email I meant to send to you and didn't get around to. What was that one about? Well, I'll have to send you the email later. But there's this general thing. Well, I mean, in a way, it's amazing that this whole game that you were talking about is really encoded just in the sheaf cohomology of this one sheaf, this sheaf of holomorphic. Well, let's see, sheaf of holomorphic functions valued in the, what am I trying to say? Sheaf of holomorphic section. Let's see. So it's the multiplicative group.
Yeah. Yeah. Invertible holomorphic functions.
It's a sheaf of all invertible holomorphic functions, and that's this sheaf that somehow participates in the exponential. What's it called? The exponential exact sequence or something like that.
Yeah, that's one of the three.
Is it the middle one, kind of? Which one is it? Is it the sub thing?
No, it's the last one. So it's like
the last one.
You should think of it as like a souped up version of the fact that the integers includes in the complex numbers, and they're the kernels. It's the kernel of exponentiation. If you do exponentiation right, like e to the t I x.
Okay, that's interesting. I'll have to think about that. Okay.
So it's basically just a sheafified version of the relation between the integers, the complex numbers, and the invertible.
Okay, let me just write that down for a moment. So it's this. So say it again. What the sub thing?
So it's like Z into C into or to C star.
Yeah. Oh, okay. Say it again. Z into C star.
Or to C star, I guess I should say.
Sure. Down to C star. Okay. So much of this I haven't really thought about yet, so I really need to think about this. But what am I trying to say? Well, again, I mean, there's different viewpoints here, which sometimes I label as highbrow or lowbrow or middlebrow or whatever. And in a way, it's amazing. I mean, I guess I'm calling the sheaf cohomology lowbrow here or something like that. But it's amazing how everything is just apparently contained in that to me. But so I think I get the impression that one of the things a lot of other people do, and I have a feeling it's the kind of thing that I'd also like to do, but perhaps maybe not in the same way. I don't know whether it's in the same way as other people, is look for more highbrow interpretations of this lowbrow thing. In terms of like categories and higher categories and stuff like that. And or even I mean, maybe n-gerbes is already one step more highbrow than gerbes and or n-gerbes is one step more highbrow than just the sheaf cohomology. But
yeah, one way people put it is that like the gerbes and n-gerbes give a well, they might call it like a geometrical interpretation of the sheaf cohomology of this invertible thing.
yeah, I'm still confused whether it really needs a geometric interpretation. I mean, is there, in what sense is it already geometric, et cetera, et cetera, et cetera. But so one thing I started thinking about was so, what if I take sort of so again, I'm thinking from the 2-rig point of view here, from the total 2-rig point of view. And I'm thinking of like the classifying stack for line bundles from that point of view. So that's basically just the representation category, the, I guess, rational representation category or whatever of GL1. And roughly speaking, and so that's a 2-rig. And then you can take some other 2-rig and you can just tensor these two rigs together, and you're getting the you're getting the quasi-coherent sheaves over this Cartesian product, which is like a Cartesian product of the moduli stack for line bundles and this other space or variety. And then you think of this Cartesian product as a bundle over this other space, and it's the trivial bundle. It's the trivial bundle of these moduli stacks. But then, I started thinking about trying to get non-trivial bundles of these, and trying to think of, let's see, I hope I'm not making too bad of levels up here, but maybe trying to think of sections of that bundle as being gerbes or something like that. And in that way, getting a particular flavor of geometric interpretation, or a very category theoretic, very 2-rig oriented geometric interpretation of these gerbes. So that's just something I've been fooling around with. I've been meaning to tell you about it. Haven't, been doing a bad job of writing it up. So I just haven't gotten around to telling you about any of that yet. So, yeah, so that, right.
What's description of the result of tensoring a 2-rig with this representations of GL1?
What kind of description of the answer do you want?
I don't know. I said the best one. That's
what you said, the best one.
There might be several best ones, but anyway, a best.
I mean, can you just for now just think of it as analogous to the decategorified thing? The decategorified thing is you have, the tensor product of 2 commutative rings is the polynomial functions on the Cartesian product of their spectrums. So, I'm just trying, and a trivial bundle is just a Cartesian product of a fiber and a base. So I'm just trying to set it up like that. I'm trying to look at, gerbes over a base, and I'm trying to think of them, again, I hope I'm not making too bad of levels up here, trying to think of them as sections of this trivial bundle, sections of the, right? I mean, there's the trivial line bundle, but I'm trying to look up one step above that, this trivial category of line bundle, or trivial bundle of the moduli stack of lines. So I'm trying to look at, one step above the trivial line bundle. So
is that supposed to be the trivial gerb.
Maybe.
It's like is it like that space? It's like
I think that's right. I think that's right. I just feel like I'm constantly in danger of falling off the level ladder here.
Yeah.
But yeah, that sounds about right. And then there's various things you could do with that. You could treat that as a 2-rig. You could look at sections of that bundle. I want to do all these things, and I want to connect them to these other approaches to gerbes that you've been describing, and many different approaches to gerbes that we've been bumping into. That I've been bumping into. What Hitchin. What he
not friend.
Okay. I'm not sure that's how I was trying to mispronounce it.
You said Hitchin. Okay.
I mean, he has some interesting sounding discussions of gerbes and this other discussion. There's a whole bunch of things to.
Mm-hmm.
And again, I mean, there's just so many things to try to learn here. I mean, this is all just a small part of all the different topics we're thinking about. But anyway, today I'm going to try to continue with trying to explain the belief method, which I started trying to explain last time. But it will help if I could do this, if I could find some notes that I had. So look a little bit. There's some notes here. Shouldn't be that hard to find. Yes, okay, I think I found it. Okay. So yeah, but this is still going to be very disorganized. Let me try to turn on some sort of whiteboard thing here. Let me do this. Okay, and then I'm supposed to share the screen or something like that. What am I supposed to do? Oh, okay, maybe still not used to this. Okay, it goes down there. All right, and then share screen.
Yeah.
Okay, I guess I can see it. I guess you can see you. That's good enough for now. All right, so let me try to pick up with the example that we left off. So it would help if I could remember the example that we left off with. So I mean, we were trying to use the belief method. Well, in particular, we were using it in the context that sometimes in a semi-joking way, I call this the categorified Grosvenor basis method. And we're looking at it in the context where it really does most resemble the Grosvenor basis method, perhaps. But that's in the context of commutative quantales. And so, yeah, we need some presentation of a commutative quantile. And we had one. And I'm just trying to relocate it here.
I can tell you what it is because it's in my last notes from you.
Okay, I may have just found it here, but yes. So go ahead.
So the free quantile on two generators, X and Y, you start with that.
Okay, let me see. I got this. Okay, so we have X and Y. Yeah. Okay.
And then you impose an axiom, which I wrote as X. Well, I wrote it in this way. X is less than or equal to Y squared plus 1.
X is less than or equal to. Okay, for some reason I'm writing it as Y tensor Y plus 1. Okay.
Yeah.
And then it looks like I have another. Oh, that's the whole thing?
That was the whole axiom system. You did derive an equation from that. I forget if that equation is equivalent to the inequality.
Well,
I don't know if it helps to turn them into equational.
Yeah, I'm really not sure. I might like it. This time I might prefer it this way. But in particular, I might like to emphasize that this is a morphism. Is that right? So I could draw it as X arrow, or I could write it as, right. I guess I should put a little tensor subscript on the unit element. Okay, so I think it's like that. And then we were trying to, figure out the syntactic category of this. So before we impose the equation, we know that the syntactic category just looks like, how do I draw it? I'll draw it. So I guess it's supposed, let's see, should I make it I've heard that the Chinese ways you have be the intersections, the Western ways you have it be the boxes.
Well, the boxes are easy to draw something in, but
let's have it be the intersections. So these are. So yes, so I guess, okay, so this axis is the first axis, the horizontal axis is the exponent of X, I guess. So it's sort of an X axis. And this is the exponent of Y. So each, it looks like I forgot or something that it was supposed to be on the, no, I guess it's right. Okay. It's just the 3 and the 5 seems somehow bad. Okay. Yeah. So, this is all these monomials, these tensor monomials. This is the grid of tensor monomials in the X and Y. And the free commutative quantile is just the arbitrary subsets of that. So in other words, a believer to start out with is a subset of this grid. But then we're going to sharpen the theory by imposing the axiom, and that's going to constrain the believers. And we're trying to understand how that works. And so how do I get this to work? All right. Oh, wait a minute. Maybe I can make this a little bit larger. Let's see. Okay, that might help. Sorry. Still flailing around here. So so I think when we talked about this last time, one of the kind of expository mistakes I made was we raised the issue of, what part of this method involves the belief? And I mean, we agreed that when you impose the axiom, you find the things that believe in the axiom. But I think you also raised the question of, what about the things, what about before that stage? Do we consider that a matter of belief? And I think I think it was my fault. I think it sort of gave the answer that maybe no, we don't really consider that. We don't really consider that part of the belief method. But that's really wrong. Even from the very first stage, you call the objects of the syntactic category the believers in whatever the theory is so far. So I guess you could even start out with at the point where it's the theory of nothing. And at that point, in this doctrine, the believers would just be, is it just true and false? Is that right? I guess that's the free commutative quantile on the empty set and the full set. Right. So there's just one monomial, which is the tensor unit at that point, and you have the singleton subset of it or the empty set. And so those are the believers in nothing. Those are the true skeptics. Unbelievers. Yes, unbelievers or true skeptics.
Pre-believers, yeah.
Yes, fodder for conversion. But then you impose belief in these two objects, X and Y. And at that point, the believers become these subsets of this grid. And again, well, what am I trying to say? I mean, you can consider the new believer to be the old believer equipped with a belief. So, there's a particular belief that makes the old believer into a new believer. And so, in other words, there's an underlying old believer. There's always an underlying old believer of the new believer. And again, that's sort of the whole way that the belief method works. We're exploiting the right adjoint to the theory morphism, and that's this underlying skeptic, underlying old believer of the new believer. And so in this case, where you're taking something that believes in X and Y, and you're looking at the underlying skeptic, that believes in nothing, it would just be, you would just take the constant coefficient. So in other words, the question of whether the unit belongs to this subset or not. Whether the subset includes the extreme corner at the upper left. And yeah, that is the right adjoint to this theory morphism. And if I did it correctly, yes. So yes, so the thing I'm belaboring at the moment is that it's not just a matter of believing in facts, or it's also a matter of believing in things. Well, believing in morphisms and believing in objects, but also believing in if the kind of facts that we can believe in could be equations between morphisms, or you could also, sometimes it's better to think of it as the existence of inverses for morphisms. Because when you supply an inverse for a morphism, you're putting in new morphisms, but it's really just a property, right? You're just localizing. So we can think, we're not thinking very precisely at this point about the difference between property and structure and stuff, but informally we can think of inverting a morphism as a kind of property. Because you really don't have any choice in how you invert a morphism. It just happens automatically. So okay. So the key idea is that belief has to do with homing into the believer. So what do I mean by that? I mean that in order to find what the believers are in any given thing, you sort of have to take that thing and you have to hom it in to the old believers, and that becomes a part of the new believers. Didn't say that very clearly, but let me try to give examples here. So let's see. So let's think about this thing, believing in a morphism, this thing right here, believing in a morphism from X into the tensor square of Y plus, and again, plus here is really just supremum because we're working in this very impoverished context at the moment to make things easier. Later, we're going to, try to depoverish the situation, but at this point, we're still doing a very toy example involving the impoverished context where categories are really just posets. So that means that these, symmetric monoidal total categories are really just commutative quantales. Yes, so that's why we're working with commutative quantales. So, I wish I knew what this was doing here, but okay. So supposing I got a candidate, do you have a metaphor, a word that participates in the metaphor for a candidate to become a belief? It's like, the guy walks in the door and he says, I want to join, or something like that.
Candidate believer or a candidate belief? Candidate believer?
Candidate believer. Candidate believer. Yeah.
Yeah.
A candidate, an old believer, that's a candidate to become a new believer, candidate to possess a belief.
I bet there is a name for it, but I don't know what it is.
Oh, I thought there is one, right? Isn't there a?
There probably is.
I mean, an applicant, but what do you call an applicant to a cult? A mark or something like that?
I don't think that's what they call it.
That's not what they call it?
Well, no, they're something nicer.
Okay. So, but I'm going to use, my typical letter, the typical letter I've always used is B. So we're going to try to take this axiom that we're trying to believe in, and I'm not even sure axiom is the best word for it, but it's a thing that we're trying to believe in here. I wish I knew what was making this jump like this. Oh, I see. Okay, it could be that thing. Okay, let me see if I can put that out of the way. Is that going to work? I'm just hoping to put this Velcro thing out of the way somehow. Okay. B is the believer. Okay. But now we're trying to, damn. Sorry, I haven't learned how to do this yet. I don't know what's causing this. So we're trying to hom our axiom into the believer. So homing into something is a contravariant thing. So our axiom is going to end up looking sort of like, backwards from the way it looks to begin with, but it's only hommed into B. So what do I mean? I mean, it's going to be like, I guess, homing from X into B. Oh, it could be that button that I'm accidentally pressing. Okay, homing from X into B. And this is going to be from homing from Y tensor squared plus the tensor unit into B. So this is sort of a picture of the belief that B needs in order to become the new believer, in order to be au courant with the latest cult. So let's see. Well, yeah, so you might be wondering what kind of Hom this is. Is it an external Hom? Is it an internal Hom? That's actually a very good question, because it really depends on the doctrine which kind of Hom this is. So it's going to turn out that for the doctrine that we're working with, which is the commutative quantile doctrine, it's going to be an internal Hom. But so what is a belief doctrine? Let's remind ourselves, a belief doctrine is a monad on the bicategory of locally presentable enriched categories over our base category. In this case, our base category is just the truth values. So we're dealing with a monad on, it's really the bicategory of cocomplete posets. A monad on the bicategory of cocomplete posets. And we're sort of thinking of that, we're thinking of it as a bicategory. You could just think of it as a category, because it's, impoverished enough, you could just think of it as a category. But I think it's better to think of it here as a bicategory. So we've got yeah, we're dealing with these monads on this bicategory of cocomplete posets, and one of them is the main one that we're supposed to be dealing with in this example, which is the commutative quantile monad. So there's a free commutative quantile on a free commutative quantile on a cocomplete poset, and basically that's practically the same thing as a symmetric algebra construction, right? If you've got a cocomplete poset, you can just take its symmetric tensor powers. I mean, there's all sorts of level slips that are easy to fall into here, but try not to. So you can take I hope I'm saying this right. Yeah, it's basically just, this sum of the symmetrized tensor powers of the cocomplete poset. That gives you the free commutative quantile on your poset. And how does that fit with the picture that we drew? I guess it's those diagonals. Is that right? So the symmetrized tensor powers. Is that right?
Yep.
Except, wait a minute, no, I'm confused. Is that right? Let's see.
Well, if you said the right diagonal, the grading.
Oh, no, I guess that's right. Okay. For some reason, I was getting confused and thinking that there was, that this grid itself had some sort of poset structure on it, but it doesn't. So yeah, it really is just these, did you say I have to draw the correct diagonals? Should I try to draw them here for a moment? So there's that's the 0th tensor power, that's the 1st tensor power.
Yep.
Etc. like that. That's right. And right, so I guess this is the free commutative quantile on a discrete poset. Or on the am I saying this right? Yeah, I'm saying all this in a very clumsy way, but yeah, if we really worked it out, it would work out correctly.
It sounds like you sort of wanted to say on a free thing on a co-complete poset.
Yes.
But then you sort of also want to
yes.
go down a bit further and do the free thing just on a set.
Yes, and these all fit together, and
yeah.
So yeah, I'm just doing a terrible job of explaining it, but yes, that's what's going on. So yes, so we are well, so first of all, I wrote this notation for what the belief is supposed to be, and so basically we from the little bit of it that we already worked out, we're anticipating that this belief is going to be a property, it's going to be a constraint on these subsets, and we have some intuition about what that constraint is going to be like. But before we get into that, let's just do a little syntactic nicening of this. That we've got, this says that we're homing. In this case, I've claimed that we're internal homing from this sum into B. So when you internal hom from a sum into a B, really most kinds of homs, when you hom from a sum, the resulting hom is itself a product. So we could rewrite this as a product here. So it should be what? Should be the product of this hom, sorry. Times, that's supposed to be a Cartesian product, using dot for Cartesian product. If you complain vigorously enough, I can use like a cross or something for Cartesian product, but that looks like an X to me. So what is this? Oh, this is, well, this is homing. The second factor is homing from the tensor unit into B. So that's really just B. So I'll just write it like that. Okay.
Yeah.
And so again, it's a little bit ambiguous or sloppy as to whether we're treating this as a structure or property or something like that. But let's try to think about it. Right. So part of the point is, can we actually understand how to perform this internal homing on our subsets? So do you have an idea how to internal hom one of these subsets into another one of these subsets?
I want to use an external hom, but I wanted to say, like, I want to see if a subset B is okay, because in this case it's just, I think, a property whether subset B is a believer.
Yes.
So I wanted this thing.
So that encourages you to think of it as an X. You would be more comfortable thinking of an external hom as giving us a truth value.
Yeah, I don't know if it's right or not, but that makes me want to do that, and it makes me want to read this thing you said is like, if y squared is below somebody in B, and
yeah, okay, let's try it that way.
One is below somebody, the unit is below somebody in B, which I guess just means that, like, there's something in B. Then X is below somebody in B.
Right. In fact, let's try it that way. But let's keep in the back of our minds that there is this sort of more sophisticated way to do it. And now that I think about it, the more sophisticated way really is fairly easy, because you've got internal homs, but then you're just saying that there exists a morphism. When you write that arrow, we're sort of saying that there exists a morphism. And the morphism is just this, well, it's this containment relation in the among the believers. Yeah. So we'll sort of do it your way, but I'm claiming that the sophisticated way really wraps it up into a very neat package. So in fact, I guess what I'm trying to say is that one way to think about how this doctrine works is that you really do use the external homs here. But then everything that you believe in, you have to also believe in I want to say that you take every statement that you believe in and you tensor it by any object, and that becomes another thing you have to believe in. So if you believe so that'd be like x times something, let's call it k, x times x tensor k you'd have to believe that that maps into y tensor square tensor k plus k. And that's how we get this pattern of the belief sort of acts in a very translation invariant way in this grid picture. Yeah, both horizontal and vertical translation. So okay, so what are you trying to say? So you're trying to help me here. You're trying to get us to understand how this actually works. So what are you saying? You're saying that if x.
Well, the implication is pointing backwards. I was trying to describe it as like a test to see if B is a believer. You may want to read, you may prefer to say like a way to construct a believer starting from a possible believer. But I guess they're not.
Well, that conversion process you're talking about, that's the left adjoint. That's the left adjoint. The right adjoint is just forgetting that we have the belief.
So anyway, as describing it as a test as to whether you are a believer of something, like saying like if there's something if B is non-empty and y squared is below something in B, then x has to be below something in B. I have a feeling
yes
the product with times B is somehow you can get rid of it in this case, because if y squared is below something in B, then B has to be non-empty. I don't know. It seems like that you could write equals y squared comma B in this.
Can you say that again? I didn't quite follow. I just somehow blanked out. Say it again. Explain the idea again.
It seems to me like you could actually get away with simplifying the thing that you're pointing at here.
Yeah.
And you could just like cross out the times B for some reason.
Cross out the times B. Why?
Because it seems like I'm reading it as if y squared is below something in B and the unit is below something in B, then x is below something in B. But it seems like if y squared is below something in B, then the unit, maybe I'm making, never mind. No, let's see. Never mind. No, that's just wrong. Never mind.
Well, okay. So let's try drawing some random subset, or maybe I'll draw some random subset, but I may have to try several different random subsets to get something to work interestingly. But let's try some random subsets and test them, and perhaps if they fail, we can try to convert them to believe. Maybe I'll just try to try this subset right here. Okay. And so now what are we supposed to say? How do we test that? You know what? I think what will help me. and I really need help here. But I think what will help me is if I really do try acting out some of these internal HOMs. So yeah, let's just call this B. I mean, maybe you already said this and I just was not following what you're saying. But let's call this B right here, okay? It's inside of that region. And when I say the inside of that region, I mean all the vertexes that are inside of that region. And we're trying, so the first thing we're trying to do is we're trying to HOM X into it, okay? So what do you think HOM X into that is? HOM from X into that. And again, okay. So now I am trying to force you to think about the internal HOM.
Yeah.
So
I think it means taking that shape, translating it one unit to the left.
That's right. And if it runs into the ground, then that just, you know,
falls off the edge of the world.
Yeah.
Uh-huh.
Right. So tensoring with X is just translating one unit to the right.
Mm-hmm.
So if you think about it, in this very simple context, it's almost like trying to undo that. And so, yeah, I think what it is, I think it's just translating one unit to the left. And if it falls off the edge of the world, it falls off the edge of the world. So what about the other internal HOMs here? Let's try, yeah, let's just try Y, you know, Y tensor square, HOMing that into B. So what's that going to be?
That's translating it 2 units up.
2 units up, right? 2 units up, that's right. And the other one is just B itself, okay?
Yeah.
And then we're saying take the Cartesian product. So in this context, Cartesian product of truth values is just intersection of subsets, basically. So we're saying, if I'm reading this correctly, it says we're supposed to take the intersection of B and the thing 2 of them up. And that should be contained in, so okay, let me try and draw the 2 of them up. So tell me if I'm doing this right. It looks like that.
Yep. So the intersection has just one guy in it.
The intersection is just one guy in it. And that one guy, we have to check whether that's in.
Hey, you didn't pick this one randomly, did you? It seems
I
like
did,
it's
yes.
You did? Wow,
yes.
Okay. I can't believe it. It's actually working. I thought you were just bound to get some stupid nonsense here, but anyway, this is
well. But I wanted to get some stupid nonsense because then we could convert the.
Yeah.
I still have a feeling there's a word for this. The applicant. The.
Yeah, there must be. I mean, missionaries must have had a name for such people because that's what they were.
Yes.
Dealing with, but I don't remember what it is.
Okay, so all right. Maybe I have another color here. Maybe I can. You're telling me it's 1 unit to the left of B?
Yep. X on B.
And it went like that or something like that? So you're telling me that the intersection of red and green is in blue,
Yep.
and that therefore this is a believer.
Yep.
Can you give me a shape where that would fail? Yeah. First of all, let me erase this, all this B, and we'll try another candidate B. But try and come up with one that's going to fail this time, so we can really violently convert it. Okay.
So leave that B there for a second. Can you
leave that B there?
Can you undo it?
Sure.
Just to let me stare at it. Okay. Like one simple thing to do, like the reason this one worked,
yeah,
had a lot to do with that upper left corner of it being in there.
Yeah.
So we could just change it by like change B's just to like remove. I mean, if this is like a minimal change, remove that upper left-hand corner grid point from B. Now it won't be a believer.
Boy, I'm still really confused about why this worked. So say it again. Remove the. Okay, so that's what you think. Let me try that.
That should be like a, a minimal way to mess things up.
So if I remember correctly, you're saying this might fail?
Yeah.
Okay. So if we right, so we're looking at the intersection between this and its things that are 2 up.
Yep. So now that intersection will be empty.
Yes. So that intersection will be empty, yes. But doesn't that make it just easier for it to be a believer now? In other words, it looks like, it looks like, the way that the thing succeeded in being a believer that time was that, there was non-trivially something in the intersection, and but it actually was.
Oh wow! Did I? Yeah.
But it had something to the right of it. How about that? Maybe you should have removed. Maybe you had the implication backwards or something. I think that is what it's already had. I'm just guessing here.
Yeah.
So let's try to remove the middle dot on the top row instead. Does that seem plausible? So it sounds like I'm saying maybe this will fail.
Okay, yeah, probably. So why don't you just go ahead and do it?
Okay, so let's put the one up above in green. So it's these 3. And it's like that, I think. So it's got that one there. Yeah. And what does X humming into B look like? It looks like
shift it over to the left one, and then now you get a hole out in the correct place. Yeah, I was somehow like doing exactly the wrong, the reverse thing. Yeah.
Right, but that was close. Getting exactly backwards was close. So what does it look like? It looks like this and this and this and like that. And yeah, so that intersection of blue and green is not contained in red. So it looks like to convert it, we just need to, so yeah, its conversion is to fill in that hole.
Yep.
But let's think more, let me try to think more pictorially about what that completion process did. So it looked to me like it was something like, am I doing it right? No, let me see if I get this right. I'm thinking that it was like that thing and that thing forced that thing. And that's the pattern.
Yep.
So let me see if I can get a little bit of a cascade going. Okay, let's see if we can find an example where to convert it, you need a little bit of a cascade. So is this going to work? What if we had, yeah, I think that'll work, right? I can get a slight cascade going.
Yeah, if you put those two blue dots in, you just did, and then some more.
Well, I was going to try. Okay, well, okay. Let me show you what I had. I had this and this and this, and so these two will compel this one here, but then these two will compel this one right here, and that was a very short cascade. But sometimes you can get infinite cascades, right?
I think you can only get, is it true that you can only get infinite cascades? You have an infinite, for this one, for this particular belief, you can only get
for this particular
cascade if you have infinite set to begin with.
That sounds very plausible because you're kind of saying it's going at that angle that's out of the main quadrant. It sounds like you're saying in order to get an infinite cascade, you need an angle of the axiom to be in the main quadrant. That sounds very plausible. You're pretty sure about that? You're semi-sure about that.
Yeah. Well, for this, I'm just stating it for this one here, but yeah, of course you can get an infinite cascade if you had an infinite set. You could just keep
yes.
Yeah.
Yes.
But
yes.
But that's somehow different. Yeah.
So let me give a let me give another example here where we can see some nice infinite cascade. Okay. Right. Trying to erase a whole bunch of stuff here. Am I doing this right? Whoops. Oh, seems to think we. All right. Okay. Oh. Try to write something on here. Let's try, for example, believing. Damn. Oh, I must be pressing buttons actually over there. Okay. Yeah, I think this is. I think I can semi-legitimately complain that it's it's maltreating left-handers, but they do have a button, so eventually I'll be able to get this problem fixed. But let's see. Let's just say, let's try to believe in one. Let's see. I want to say like 1 is less than x or x is less than 1 or something like that. Let's see. So what did we have? We had something. Okay. Well, let's see. X. Right. What if you had x is greater than 1 or something like that? So 1 is less than x. Is that right? I hope I'm reading that correctly as 1 is less than x. And again, this is the tensor unit. Let's try thing here. Okay, so what are the believers? I mean, is this a believer? And if it's not a believer, how do you have to correct it to become a believer?
So this is saying,
yeah.
Let's see, there's this contravariance that's confusing me. This is saying something like that if a dot is in there. Well, just guessing from what you said, then it's translate to the right one must be in there. But let's see, why is it to right?
Yeah. Let's write it. Let's write out the
that.
belief. Let's write out what the belief looks like. So the belief looks like B X homing into B. So X homing into B is the leftward thing. So it's saying what? That it's saying that if you're is this coming out backwards? There's somehow, let's see.
I don't think this is gonna, yeah, I was worrying about this contravariance.
How did I manage to make the mistake then? I forgot about the contravariance of belief. Is that how I did it?
Maybe.
So let's see.
So this will do.
Yeah.
Wait, let's see. So this is saying that if you
move it to the left,
if moving to the left puts you in there, then you have to already be in there. So this will keep generating new dots to the left of every dot you already have in. That will end at so that will do stuff, but it will just define.
Yeah, that's not what I wanted. If
So,
I must have screwed it up somehow, or else we're both screwing it up now. But yeah, so okay, so
it looks like it's just exactly backwards.
It says right. It looks like it's just exactly backwards, right? Yeah, I think we can. I think we can declare a little bit of victory here. In principle, we could figure it out. I was trying to get a cascade going the correct way, and I screwed it up.
Just turn around that. Well, anyway, just turn around that action.
Sure.
I mean, if you call that, it sounds like you want to declare victory without having, but you don't want to fight the war.
I'm just not sure I'm
because you might not win.
Let's see. Right. Oh, well, yeah, I erased too much here. Let's see. I just wanted to erase that one arrow there. So, okay.
Yeah, well, you got to use an eraser for that. But...
Damn. Why did it get erased? Okay. Damn. I'm not very good at this. I really should try flipping it. Let's see. Well, I'll try faking it for now. So, okay. So it would be B is contained in B is contained in its leftward shift. Is that right?
I think did you turn around the arrow or not? You shouldn't have erased the stuff you had.
I think this is just a single negative sign compared to the previous one. I don't think I did, a double negative.
So B is contained in its left translate.
Yes.
Oh, yeah,
So it has to be buffered from the right in order that it's contained in its left translate. I think that's right. Yeah, I think that's right.
Okay.
So yeah, that would, yeah. Yes. So okay. So yeah. So we're pretending that we really understand all of this commutative quantile stuff. in general. And we have some sort of superficial, maybe more than superficial resemblance to Grosvenor basis methods. But let's think about some other, let's try to think about some other ways of thinking about this. So what am I trying to say? Well, so we do have, in this context, we have the general idea. It's very plausible, even if we're not being very careful about it. It's very plausible that these theories that we sketch, in some sense, these commutative quantiles, you can think of them as some weird kind of propositional theories, perhaps. I mean, you can think of, the X and Y are like objects, and then the axioms are like morphisms. There are other ways to think about it. Let's see. What am I trying to say? That if you have well, right. So let's just focus on let's focus on the thing we're calling the axioms or the morphisms or something like that. The other thing is just these generators for the commutative quantile, and that just tells us the dimensionality of our grid that we're taking subsets of. So let's pretend that we've already put in all the generators we want. We're not going to put in any more generators. From this point on, we're just going to put in these things we're calling axioms or morphisms or whatever. And so when you do that, you can always think of that. It turns out to be true, and it's very convenient. It turns out that you can always think of the left adjoint here, the conversion process. Well, you can always think of the whole adjunction here as the adjunction coming from a monad. So that, in fact, what we're really doing is where you can think of those axioms that we wrote down as, or those let's call them morphisms. You can think of those morphisms that we're writing down. Those are generating operations for a monad, right? You can think of a monad as a kind of operational theory, right? A monad is sort of generated by operations. There are other operations. Perhaps one of the best ways to think of it is that a monad always has a Kleisli category, and the Kleisli category is, an extension of the original category that the monad lives on, and so it has the original objects, but has new morphisms in it. And you think of those new morphisms in the Kleisli category as being operations. And there's some funny contravariance tricks here, depending on, which way you think of the Kleisli category, which way you think of the morphisms in the Kleisli category as pointing. I guess if you think of them as pointing the same way as they're in the original category, well, they get reversed when you think of this as operations, but that's exactly because of the belief method, the contravariance of the belief. So, anyways, what I'm saying is, okay, so I didn't say it very well yet. Maybe I could say it a little bit better. That the new believers, when all you have is these new morphisms, the new believers are just algebras for a monad. That's what these believers are. They're algebras for a monad. And the monad is described by, the monad is, in this particular context, we give the generating operations for the monad. And those are the axioms that we were writing down, that we believe in, or those morphisms that we're writing down. Those morphisms, when you look at them the right way, I forget which way is backwards, which way is forwards, but they're basically Kleisli morphisms. Right. So right, when you write them down as morphisms, they're just that's the forwards direction. But when you turn them into beliefs, those are the operations. So they're arities, right? You know what I'm saying? Like in the Kleisli category for the monad for groups, you have this, am I saying it right? You're putting in this morphism from 1 to 2.
Mhm.
But when you read that as an operation, it's going backwards, right? This morphism from the free group on 1 to the free group on 2.
Yeah.
That's, it assigns to the generator the thing that you get by multiplying the other two generators. The operations go backwards. The binary operation of multiplication in a group that goes the other way. So that's an important part of how to understand this contravariance of belief. It's exactly that contravariance of reading the morphisms in a Kleisli category as operations going in the other way. So these beliefs are these operations, really. Or these whole algebra structures, many operations can combine together to give you a whole algebra structure, and that is a belief in something. And so that's what's going on here. Now, there's one very important trick that's very important for this particular doctrine, and that is that these monads that we're dealing with are commutative monads. Again, I think one way to think it. So there's a definition. Let me give you a sense of what a commutative monad is. Okay,
These are also idempotent monads in this special case, right?
Yes, that's right. That's purely a matter of impoverishment. When we depoverish, it's going to be really interesting that we're getting non-idempotent monads. Yeah. Right. So these idempotent monads are really just closure operators or something like that. That's right. That's right. But that's, it's good to anticipate to some extent what's going to happen when we depoverish.
Right.
You get much more interesting monads.
So why are they okay? So anyway, I had to say that. I just had to say that. So
yes.
So why are they commutative, and what? That's special, or is that always going to persist?
Well, what it is, if we were working right, okay, right. One of the things I forgot to say is that we could have done this whole thing. Remember, there's a very trivial example of a monad on the cocomplete posets, which is the identity monad. So the theories there are just cocomplete posets. So that's just the doctrine purely of supremums, really. The doctrine where the only thing you talk about in the syntax is supremums. So that's the base belief doctrine, if the base that you're working over is this impoverished base of two-thirds. And in there, you just take arbitrary monads. So, if we were working with that base doctrine, then we wouldn't have this grid in that case, right? The grid is arising from the tensor products, right? But if you don't have the tensor products, so all you have is the supremums, then there's no grid, right? I mean, what is, you put in generators, and then the only thing you can do is you can take subsets of the generators. Instead of subsets of the monomials, you just take subsets of the generators. And then you take arbitrary closure systems on that, arbitrary monads on that, right? The arbitrary monads on these posets are idempotent monads, but those are just called closure operators sometimes. And so if you're working in that really low-level doctrine where there are no tensor products, all you have is the colimits, all you have is the supremums, then arbitrary monads give you these theories, give you these axioms, and so you're just taking the closed things for an arbitrary closure, the closed sets for an arbitrary closure operation. Whereas there's this much more entertaining doctrine where you have the symmetric tensor products, and so that's what gives you the commutativity. So, I mean, I'm sure if you look up in the n-lab or somewhere, if you read up on commutative monads, you'll find like the main theorem of commutative monads. There's 10 different flavors of this main theorem, and 9 of them I don't like, but I'm sure you can find the one that I like in there somewhere. I mean, you know, without the fine print, the fundamental theorem of commutative monads says that the algebra category of a commutative monad is very special because it automatically has a tensor product on it. It automatically has a symmetric tensor product on it. And there's, you know, there's a whole bunch of different variations on this theorem, but that's the basic theorem. So that's what's going on here. So if you just take, you know, if you start out with a category and it has a beautiful symmetric tensor product on it, but then if you take the monads with respect, then you take the algebras with respect to a non-commutative monad, the new category won't have a symmetric tensor product on it anymore. Generally, that symmetric tensor product will be completely obliterated, completely destroyed by taking the algebras with respect to that arbitrary monad. But if you take the algebras with respect to a commutative monad, then the original tensor product survives, and the formula, right? So it turns out, yeah, I mean, you can prove this fundamental theorem by just, you know, follow your nose kind of thing if you do it right. But basically it says that to get the new tensor product of the new believers, in other words, of the algebras for this monad, I hope I'm saying this right, you just take the old tensor product of the new believers, and then you convert that. And that will automatically be that will automatically function as a new symmetric tensor product on the new believers. Whereas if the original monad had not been a commutative monad, that idea wouldn't have worked. So
you take two algebras, and to tensor them, you take their underlying things and you tensor them, and then you freely
convert
by the free functor.
Yes, then you convert to the cult belief, and that will automatically be a symmetric tensor product on the new believers. I mean, does that remind you of some situations, like if you take right? I mean, you're probably already familiar with this. If you take the free group monad on the category of sets, then that's not a commutative monad, and right. You won't get, at least in this way, maybe not in any way, you won't get any good tensor product of the groups. But if you take a commutative monad, such as the monad for abelian groups, then that will be, you know, then the algebras for that will form a symmetric monoidal category, and the tensor product will be given simply by. Am I saying that right?
It doesn't sound right. It doesn't sound right. Because you're making it sound like that. That's what I'm getting worried about. Okay.
Like
the tensor product of any abelian groups has to be a free abelian group.
Okay. So maybe I didn't say it right, but it's very close. It's very close.
Okay.
What am I trying to say? So
you have to do a co-equalizer of what
yes. So I obviously set it up in a screwed. I set it in a screwed up way. But there's something sensible you can do. Yes. Right. It's good we did think about this example, because if you think about this example, it tells you how to fix the screwed up thing that it said. So yeah. We'll have to think about what is the right way to do that. But when you do it the right way, you do get the algebras of the commutative monad to be, you know, it could have been, you know, maybe I had that impoverished case on my mind. Maybe what I said actually works in that impoverished case. Where it's just posets or something like that, because then those co-equalizers are, you know, just swept under the rug or something like that. Maybe, but if you think about that example, then that example of the abelian groups and how there's a commutative monad for abelian groups on the category of sets, that should be, that one example is probably good enough to get the intuition for how the whole thing works. And again, one of the key things is that this adjunction, these adjoint, the left adjoint of the adjunction, when you do it right, will be a symmetric monoidal left adjoint. So in other words, it'll be a theory morphism. And that's the whole point. That's the whole point, that the left adjoint will be a theory morphism for this doctrine. It'll be a symmetric monoidal left adjoint. And again, we see that when you do it the right way, not the way I started out saying, which was totally screwed up. But when you do it the right way, taking the free abelian group on a set, that's a symmetric monoidal left adjoint, a strongly symmetric monoidal left adjoint from Cartesian product of sets to tensor product of abelian groups. So, a lot of things happen in a very beautiful automatic way that you get the new tensor product in the theory when you do it the right way. So, so we actually still have some time here to actually try some of the depoverished case. Some of the depoverished case. So, I mean, we still need zillions more of examples, right? You need some examples where you're just kind of like picking silly examples and working them out and seeing how the method guides you to do it in the right way. But then you also need another flavor of examples of, well-chosen examples. Right? The method has to work even with the ill-chosen examples, but then you also need some well-chosen examples to show why all the good things that you can get with the method. So let's see. So we're going to depoverish here, which means just we're going to work with, instead of working with symmetric monoidal cocomplete posets, we're going to work with symmetric monoidal locally presentable categories. So again, I vacillate sometimes between symmetric monoidal total categories and symmetric monoidal locally presentable categories. The locally presentable categories are a very tame version of total categories, and I'm not quite expert enough to know what happens if I really allow us to work with the total categories. So I'm thinking about symmetric monoidal locally presentable categories.
Do you know a total category that's not?
Todd told me.
Locally presentable.
Todd told me one. It was something about topological spaces or something like that. I forget.
Yeah.
But I honestly don't remember, and I would get myself lost.
Yeah.
Probably if I start worrying about that right now. So, but Todd's a real good.
Source. He loves total categories.
Sure. Yeah. So, I have a feeling that total categories is the right way to go, but it's a little bit too difficult for me to understand at this point. I mean, what you need is really good adjoint functor theorems, I think, and I'm not sure I understand the adjoint functor theorems for total categories, but I pretty much do understand the adjoint functor theorems for locally presentable categories. So, right, I mean, I guess we could take the attitude that impoverishment is practically a functor, probably is a functor, and depoverishment is, just sort of going against the current, and so it's not really a functor, right? It's just so, but nonetheless, we can take that attitude that we're going to try and depoverish our example here. So, I mean, we could try this example of we could try this example that we've got written down, and we could just try to interpret it in this depoverished doctrine. So now we're working with symmetric monoidal locally presentable categories, and we're trying to take, again, so it's the theory of what? Theory of two objects, X and Y, and the axiom that there's a morphism from X into the tensor unit.
Mhm.
Well, so let's try thinking about this. Let's try thinking about this. Actually, you know what? Let me give you an interesting example here. Okay. I mean, well, maybe we should try. Like I said, you know, you should try both stupid examples and nice examples. I think the one I have written down at the moment on the screen is a stupid example, although it might actually be an interesting example. But let me give you an example of an interesting example that you could look at. This, I mean, this might turn out to be a very interesting example if we exploit it in sufficiently interesting ways. So one of the examples I have in mind is, let's take two generators, two generating objects, X and Y. And let's make them adjoint to each other in this symmetric monoidal category. So you can talk about, you know, objects being adjoint in a symmetric monoidal category. So this is a potentially very interesting example, I think. That's a potentially very interesting example. But let's just try this example that we have at the moment. It's written down with one. It looks like we're putting in a morphism from. You know what? Let's try it. In fact, let's just take one generator X. Okay, let's just try one generator X, and let's put in this morphism from X into the tensor unit. And I guess I should give it a name now, right? When we were working in the impoverished context, things didn't need names.
Yep. Too poor to afford names. Yeah.
But now, right. Yeah, that actually does happen, I think, in human culture.
Cannon fodder.
What?
Just cannon fodder.
Something like that. I guess I can just call this M or something like that. M for morphism. So
what's funny about this to me is that
yeah.
We sometimes in the old days you talk about like line bundles with a section, and that'd be like an object X with a morphism from 1 to X. This is like the opposite thing. And
it's very hard to tell. It's very hard to tell with line objects because.
Oh, is it true? You take the dual? Yeah, okay. The adjoint, yeah.
Yeah, and it's hard to figure out which is the best philosophy about which way you should think of them.
Oh, really?
So the morphism that's going.
Okay, but yeah, so you're making, well, okay. We're not asserting that there are duals in it yet.
Right, not yet.
But
not
this
yet.
Is
Yeah. So yeah, I very well may change my mind about what example we're doing, but for the moment we have a morphism from morphism called M from X into the tensor unit, and so we're trying to sort of cumulatively sketch out the whole syntactic category of the theory. So step by step. So before we put in the morphism M, we just have an object X. And luckily, we just happen to more or less know the answer to that, what the syntactic category is. Right? It's what I call the structure types. I guess some people call it the species of structure or something like that. but that's a symmetric monoidal category under this, convolution. Is there a name for that convolution operation? Right. It's the tensor product of two structure types is a new structure type. A new structure consists of splitting the setup into two pieces. The structure of the first type on one piece, something like that.
Yeah, it's called, not that you want to remember apparently, but it's called the Cauchy product of structure of species.
Okay.
It's one of these ones, or just a convolution. Well, they're
right. It's
a little ambiguous, but
right. But it's a very natural kind of day convolution. Are you telling me that this name Cauchy product more or less goes back to Joyal's paper that more or less started the theory? Is that what you're telling me? I don't know.
I don't know actually.
Okay.
So somehow or other, people like to talk about the Cauchy product and some other one, the Hadamard product.
Yes.
Which is the Cartesian product.
Yes.
And it took me forever to remember those terms because I don't understand why they are what they are. Yeah, I should at least figure out why they're called that.
You mean historically?
Yeah, well, someone must have ex post facto.
Hadamard really
is like this.
Well, Hadamard really did do things sort of like that. Like he had, he had a product of multiplying two matrices together entry-wise or something like that. That's like the Hadamard product of matrices or something like that.
Okay, well, that's interesting. Yeah.
Well, as usual, don't trust me on any of this, but so we've got the structure types. Got the structure types. So I guess we still didn't really say very explicitly, how can you tell when a monad is commutative? That'll be important. We'll have to say that at some point, but I guess we didn't really say it. But it has to do with, there's a certain sense in which the operations commute with each other, but it might not be your first guess as to what it means for operations to commute with each other. It very much has to do with the tensor product of objects. That's sort of when you're tensoring objects together, morphisms can sort of go along for the ride, and they do so in a very nice way, and that's called the commuting of the operations in the monad or something like that. That's a very poor description, but when we need to, we'll really need to work out what it really means for the monad to be commutative. So let's see. So what have we got here? We've got, So we've got the structure types. That's ours, and the Cauchy product of structure types. That is the walking object in this doctrine. That the theory. Yeah, the theory of an object, or in other words, the walking object in this doctrine. And now we just have one more step to go, and that is we want to adjoin a morphism from X to the tensor unit. And so, I guess it's already written down there. So it's kind of saying B, there's supposed to be an arrow from B into Hamming from X into B. So do you know what Hamming from X into B is in this case now? Right. I mean, right. We're just trying to deimpoverish our previous description.
Yeah. Believe it or not, I never learned it until my student Christian told me about it. That this is something that I did know about, which is this differentiation of species.
Yes, that's right.
I for some idiotic reason, I never had thought about the internal hum of species, and so I hadn't noticed the differentiation, which I love. Like it's related to the canonical commutation relations. We talked about that a lot. Never noticed that was just like the internal. So now we can say that position is, or the creation operator is is tensoring with X, and the annihilation operator is internal Hamming from X, which is sort of cool.
Yeah. So if you combine with what you're saying there with what we're doing here, then you're sort of hinting at something there. You're hinting at a very tempting idea that I haven't completely gotten this idea to work yet, at least not in the most general case. But you're sort of hinting in a suggesting in a hintive way, that we may be able to think of the believers in this context as the solutions to a sort of categorified differential equation.
You know, this big fat red book of species by Labelle, Bergeron, and something.
They certainly do look at categorified differential equations.
Yeah, and
I don't know how I know that because I haven't really read that book much, but I'm pretty sure that that's true. Yes, go ahead.
Yeah, and so their solutions are these the buzzword they use is like tree-like structures, which I guess is it like you have like different operations for getting new things from old, which so you like generate a tree, but it could be like a tree with multicolored branches. You're trying to describe a species.
Yeah, so I think we should be mentally prepared for the possibility that something like that may turn up in what we're looking at. We may find that some of our categories of believers have a sort of tree-like interpretation like that, but I'm not sure yet. I think it does happen, but maybe only in particularly beautiful cases or something. We'll have to see. We'll have to see. But it's an idea to think about. So, so basically, what we're saying is that the syntactic category that we're trying to construct, an object in the syntactic category that we're trying to construct, it consists of a structure type B, together with a morphism from B to its derivative. And am I saying this right? I want to say that operation has to commute with itself. Now, you're probably used to situations where things automatically commute with themselves. But for this kind of commuting that we're talking about, things don't automatically commute with themselves. So like, yeah, I mean, I'm just as a silly suggestive example, the binary operation of multiplication in the theory of groups, that does not commute with itself. If you force it to commute with itself, then it actually becomes an abelian group, and then that commutes with itself. And this sense of commutativity, it really has to do with sort of this particular one. It's like a center for exchange. You've got four things, and you can first multiply in the horizontal direction and then multiply in the vertical direction, or vice versa. And it's actually a non-trivial property to get that to happen, to get the operation to commute with itself in that way. So we're looking for that kind of operation here, that kind of self-commutativity here.
Does that get forced by the fact that this map from B to X comma B came from a map from X to 1?
No, it's really just forced by the doctrine that we're working with. In the doctrine that we're working with, the symmetric monoidal doctrine, all of these monads that we get, they're all commutative monads. And and they're actually they're commutative enriched monads. Maybe I should have mentioned that. They're enriched over the structure types. So yeah, so we're going to have to understand what this means. We're going to have to understand what this means to have, but I mean, in some sense, we've just given a complete answer. I mean, in some sense, we've just given a complete description of the syntactic category. And in principle, everything you want to know about this syntactic category, including the new tensor product on it. All it is the algebras for this monad generated this commutative monad generated by this one operation of, it looks to me like it's got co-arity of X. And if, yeah, I think that's what it is. So these operations, generally, we're used to operations in a monad that have arities. But when you start doing monads on general categories, they can have co-arities as well. That the morphisms in the Kleisli category can be, you know, can go from an interesting object to an interesting object. And that means that the operations have an interesting arity and an interesting co-arity, which we're not used to operations with an interesting co-arity. I think what's going on here is that we have, it looks to me like the operation here has arity, trivial arity. It's just, you know, the tensor unit, but we have non-trivial co-arity in this case, if I'm not getting it backwards here. Yeah, yeah. But, you know, this is all just verbiage that we have to understand in order to understand, really understand what this syntactic category is. I mean, but I'm claiming that we already have the answer here. We just have to understand it. And another way to say it is that we have to understand what it means to have these. I mean, we're just putting in, instead of saying that we're taking the free commutative monad on this operation of this arity and this co-arity, we're saying that we should put in one operation M into a monad, not necessarily commutative, but then we should have it commute with itself. I mean, that's all you need to force this monad to be. I think that's true. I've always been assuming that all along. I'm pretty sure it's true. I tried to convince Martin Brandenburg that it's true. That basically, to make sure you have a commutative monad, you just make sure that all the operations that you put into it commute. They all commute with each other. But as a special case, they have to commute with themselves. That's a special case of them commuting with each other. Okay. So in our remaining 10 minutes,
I'm familiar with, by the way, just so you know, I'm familiar with like commutative operads, which are certain. Well,
I suspect that those are related. I suspect that those are related.
I think, yeah, I mean, and well, even more related would be like commutative Levier theories, which are commutative.
Yes, absolutely.
Finitary monads, and then you can.
Yes.
But those are situations where you have operations that have arity n, some natural number, and output arity 1. And so, right. Yeah, then I know how these commutative laws look like in terms of trees, where you have like a bunch of operations all the same on top of your little mini tree, and then some other operation on the bottom is equal to switching them around, so you have like a bunch of the other operation on top and the one on the bottom.
Yes, yes.
So yeah.
I don't think it's going to be much worse than that, but we do have to take non-trivial co-arities into account. But I still think that the moral picture that you're describing should still morally work.
So one thing
Sorry, I can't hear you.
Why do these monads have to be commutative? So I mean, you don't have to do it now, but maybe I'm supposed to have seen why, but I don't.
Well, I already blathered a little bit about why it has to. It's because of, you know, we're working in the doctrine of symmetric monoidal. We're working in this doctrine that has tensor products. So, you know, these monads have to get along with the tensor product. And when you work out what it means for the monads to get along with the tensor product, it means that they are these commutative monads. So, right, in particular, with that thing, with that thing that you defined for the commutative Levier theories, notice that your little commutative square that you're doing, it involves multiplying arities together. That's the tensor product of the arities. So you have to, you know, think about tensor product of arities, but also tensor product of co-arities, and you also have to tensor product the arity with the co-arity, or something like that. That's how you get a commutative square that is a commutativity condition. Again, I'm blathering here a little bit, but it will work out very nicely when we understand what's going on. And right now we're just trying to finish up like about 5 minutes or so. And I think I'm going to have enough time to give you a sense of what's going on here, but then we'll have to, really, learn more about how it really works in future episodes. So what am I trying to say here? Yeah, I'm trying to give you a very intuitive hint about how this is going to work. So let me tell you my guess for what it's going to mean to have. What does it mean for a structure type to be equipped with an operation like this? So let me tell you what I think it means. So first of all, I get horribly confused. I get horribly confused by the contrariance of belief. But modulo that confusion, I think what we're saying is that it's something like we're going to have a structure type equipped with how do I say this? It's like a structure type equipped with an annihilation operation. Or if I got it backwards, then it's actually a structure type equipped with a creation operator. So like, what do I mean by that? So like a structure type equipped with a creation operator would be something like if you have a structured set, and if you add one more point to it, then you automatically get a new structure of the same type on this extra set. Now, I guess the way annihilation things work, I guess, is that you get to choose which one you're going to annihilate. Right. So it really does it vaguely reminds me of things that we actually know about. Like, if you think of if you think of a topology as a structure on a set, then there really are things that you do to like, right? That is like, I mean, I'm not saying yet that this has the right kind of self-commutative annihilation operator on it, but there is some sort of annihilation operator on the structure type topology. And a lot of the structure types that we're sort of familiar with from actual mathematical practice have annihilation operators on that you can take a topological space, you can just choose any point you want to throw away, and there's automatically a topology on the remainder.
It's commutative in the sense that if you first do that to one point, first remove a point X and then remove a point Y, you get the same topology as if you first removed Y and then X, I think. Yeah, I think that's true. So that might be the commutativity.
Right. I mean, the last time I thought about it, I honestly can't tell you whether that's exactly the right kind of commutativity. Maybe that is the exact right kind of commutativity. But it's going to be something like that. So these beliefs on structure types are going to be little things that say that if you can find a certain configuration in your structured set, then you can sort of operate on that configuration to like maybe change it into a different configuration or something like that. And the initial configuration is like the arity, and the final configuration is the co-arity or something like that. So for an annihilation operator, it's like the initial operation, the initial arity, the initial configuration is just a single point, and the final configuration is just the empty thing. So it's completely annihilated. But you may have more interesting kind of, operations, sort of, right? You may have some sort of funny transmutation operations on a structure type that say that you can, maybe remove 3 points and replace them by 5 points or something like that. I mean, I'm going by very vague memories, very vague intuitions. We're going to have to actually work this out to see what the actual beliefs are.
The arities can be in general structure types, right? Not just like numbers of points.
That's right. But we've already been playing around with examples where the arities are very the arities are very monomial in flavor. And I think those are the ones that are going to become close to meeting this ideal of having the believers be solutions to a categorified differential equation. I think as soon as we start getting the arities and co-arities to be general structure types that are themselves co-limits of monomial structure types, then it's going to be a lot harder to squint at it and look at these things as categorified solutions of a categorified differential equation. But maybe we will, maybe if we really enlarge our notion of what a categorified differential equation is, maybe we will still maintain that intuition somehow. But I think you're right. We're just about to quit this. I think you are, despite my awful expository style, I think you're getting some sense of what's going on here. And you really might want to think about it. It should really be interesting to think about this example. I'm not saying you should do this for homework or anything like that, but when we actually work on this, it's going to be very interesting to think about this example of the theory of an adjoint pair of objects, throwing in two objects, X and Y, but then forcing them to be adjoint to each other. I mean, it means putting in a unit and a co-unit or something like that. And we have to believe in the unit and the co-unit, but it will automatically materialize just by our faith in its existence. That's how that's the insane way that the delusional way that the belief method works. So probably all sorts of things I'm forgetting to say, but we're kind of out of time. Anything we should do before we quit? I guess one thing I just really want to cover all these other topics too. I really want to cover this topic, but I'm really interested in all these other topics that we've been talking about, the gerbes and everything like that.
So,
theoretically, this is supposed to help us understand the gerbes and stuff, but we'll see. We'll see how it goes. Yeah, that's right. Go ahead. Again, I can't hear you all of a sudden. Like you're frozen.
Do it this time, but I will sort of want to do it next time, which is to I can probably do it better next time. Which is to show you why these n-gerbe should basically walk you through Francis's argument about why these higher Néron Severi groups are what they are, because that argument doesn't require a whole huge amount of know-how. So anyway, it's sort of like
I think I really need to think about this exponential exact sequence. I mean, I've already thought about it a little bit, but I think I thought about it at a time when I had so little background in what was really going on that I could only get a limited amount out of it. But now that you're giving me some hints, I think if I just begin to really think about the exponential exact sequence in terms of sheaves and sheaf cohomology, I'm hoping that will really help when I try to understand what you're going to tell me about Francis's approach.
Yeah, so one possibility is that I could try to do what I've successfully managed to do in some of our previous conversations, whereas I like fairly efficiently tell you a bunch of stuff and you like restrain yourself from doing what you will want to do, which is say like, oh, I need to understand the exponential exact sequence much better before I really understand this.
Sure. But did you just trick me? Did I trick myself? Did I trick you? That I thought we were planning for you, or to this time you were going to tell me something, and somehow I managed to take the whole time this time. How did that work out?
Well, okay. Well, I guess I don't know. You tricked me, I guess, because I wanted to do it, and we'd never agreed on whether I would do it, and then you didn't.
I think I just totally forgot. I think I just naturally so much wanted to talk that I totally forgot.
I sort of thought that's. No, at the beginning I was sort of hinting that like maybe I was getting ready to say like I could talk about it at the end, but anyway.
All right. So to try to deal with that problem, so next time, maybe you should start next time, and
we can do it next time. And I realized
you should have. I'm claiming now to try to blame you. I'm claiming that you should have really reminded me like what time I should try to finish by.
Well, we
something
didn't,
like that.
yeah, we didn't plan that out, but
Yeah.
anyway, when I was preparing at the last possible second,
Yeah.
there's like one bit of the argument that I didn't understand. So I can.
So maybe it's not,
better
maybe it's
next
not that
week.
bad. It's not that
Yeah,
bad.
that's
If
why I
accidentally-
didn't. That's why I didn't fight for my rights. Yeah, I thought like,
That honestly makes me feel better. I didn't deliberately screw up, but
Uh-huh.
that honestly makes me feel better about it. Okay. Anything else? So there's all sorts of email I'm supposed to catch up on. I'm way behind on email.
Yeah, no, this is good. Yeah, and I understand this belief method stuff tons better than I did last time.
Sure, that's good. That's good. Again, I feel like I'm doing a bad job, but I don't feel like I'm doing that bad a job. It seems like, well, in particular, I find myself, of course, relearning much of it that I'd forgotten. So that's very helpful to me. And in fact, so I'm not sure I planned it that way, but Todd and I actually were talking about a slightly different aspect of it. And that was really tying over in helping me in this discussion as well. I always hope that the overlapping discussions will synergistically help me to understand what's going on. And that's happening a little bit. So
I'm sort of hoping and expecting that in a while you'll get to some more visibly algebraic geometry flavored examples of this.
Yes, but I claim that we're practically on the doorstep.
yeah, except that no one else, most people wouldn't see that, but yeah, okay, I mean, yes.
We really are, yes, we really are. Okay. Okay, so I guess that's it. Anything else?
No, that's it.
Okay, so thanks a lot. This was great.
Yep.
Okay, bye.
Yep, sure, bye.